thank you for making the time to come to Austin, Texas during the South by Southwest weekend. I know it's a tough weekend to get out here.
Yeah, absolutely. Thanks so much for having me out. Really appreciate it.
Yeah, look, this is one of these topics that I think there's not a listener that we've had in the past that wouldn't want to sit down and buckle up and listen to this one, right? Because we talk about technology from so many different aspects, energy, human resources, and power and people. But you and I are going to be doing a panel during South by Southwest at our after party regarding the last industrial revolution. We're addressing national security when it comes to energy.
Right.
Do me a favor, Derek. Introduce yourself to anybody that doesn't know you, and let them know who you are, and then we'll start from that. Is that fair?
Yeah, absolutely. Yeah. So I'm Derek Gaston. I'm currently a senior advisor at the Department of Energy, Office of Nuclear Energy. So I'm directly an advisor for the Assistant Secretary of Nuclear Energy there. My background is pretty varied. So I started off kind of serious tech back in the
Where are you from?
early
How about that?
2000s.
You're from Dallas or something like that, aren't you?
Well,
Born in Texas?
I was born in Dallas and then kind of grew up in Missouri.
Okay.
Yeah. So I'm from kind of central part of the world,
Okay.
central part of the U.S.
Were you an athlete? Were you a student? What were you? A little both?
I was a little bit of both. As you can see, I'm a pretty tall guy.
Yeah.
So I played football, basketball, baseball, all the things growing up. And then, but as I got into high school, those things kind of fell away a little bit versus academics. And I did debate in high school, so I was pretty into that. And yeah, kind of focused
I
more
could
on
tell
that
at
end of
lunchtime.
things.
I could tell from lunch that you took that class. No, I'm joking. Go ahead.
But yeah, sorry about that.
No, but you started. It sounds like your passion for your interest in innovation and technology took hold of you, and that's what really got you down this wormhole because you're pretty deep on a few things.
Yeah, absolutely. I think growing up through the 90s and seeing kind of the revolution of computers infiltrating every part of life, right? And especially as they first started coming into our houses and everybody started using them daily, and then the internet coming along, it was obvious to me that the best place to be was going to be using computers and developing the, capabilities using them, right? And so from the very first moment I touched a keyboard, I was hooked, right? And so I did everything that I could to use a computer every minute of every day, right? And that kind of drove me all the way into my first college experience at University of Missouri Rolla, where I went and got a degree in computer science. So and so that's kind of the background I come from, is just trying to take computers and apply them to any problem that I can find, right? And, going to an engineering university like University of Missouri Rolla, I also had to take a bunch of engineering courses at the same time, even though I was in computer science. And so that really showed me that if I could take computers and apply them to real world problems, like problems that engineers need to solve, then I could have a pretty big impact on the world. And that's the thing that kind of has driven me all the way through my career.
That's pretty awesome.
Yeah.
So when you graduated from that, did you go right into the workforce, or did you go get back to school and go get some more advanced?
I did. I had done an internship at Sandia National Lab while I was getting my bachelor's, and I was fortunate enough to get them to hire me right
so
after.
People know Sandia National Lab is a big deal. Tell them what it is. Tell them what they do there.
Yeah. So Sandia National Lab is one of the national labs in the. Let's see. Sandia National Lab is one of the United States National Laboratory labs that was originally part of the Manhattan Project that built the original nuclear weapons.
That's what I was wondering. Like, people don't realize that's where the OGs all started from. Sandia.
Yeah, absolutely. And a lot of those laboratories, Sandia, Los Alamos, Livermore,
and
Oak Ridge, they still exist, and they're still carrying out that nuclear weapons mission. In fact, they do a lot of other things these days, particularly working in energy as well. But they are. Sandia, for instance, every year prepares a letter that says our nuclear stockpile is still going to work next year.
Sure.
So they still play a critical role.
Where is Sandia National Labs, by the way?
It's down in Albuquerque, New Mexico.
Okay, so you did your first internship with that, and that's what hooked you on the energy side, or?
Well, again, if computers were my life, they were everything, right? And so there was nowhere better to go than in the national lab system, where they have the biggest computers in the world. So for the last 20 years or so, the U.S. national labs have owned literally the biggest computers in the world. And so the chance to go work with those computers and program them was really something I couldn't pass up.
Is there anything about that type of technology, probably not, that you're allowed to talk about to us? Because I think that most people view advanced technology as the consumer's playground, where in many respects it's built first for and funded by a government for some element of national security or defense, typically.
Yeah. Yeah. So yes and no, right? So the national labs kind of have a little bit of a dual purpose. So there's definitely always um, a security perspective on everything, right? National security is really a big mission in the national labs, but there's also a basic science component too, as far as wanting to advance science for all of humanity, but also specifically for the United States, right? And so there's kind of these dual missions, and sometimes those are opposed to each other in various ways. But for instance, the national laboratories is where we first we're able to come up with a lot of the basic properties that drive nuclear energy, right? And we didn't just keep that to ourselves, right? We opened that up and opened it up to the world so that the world could utilize nuclear energy because it's such a groundbreaking capability, right? So the labs are always working on basic scientific breakthroughs that make their way out into the public, either through scientific papers and publishing or through spinning off startup companies, for instance, that utilize those technologies to advance the U.S. economy. And then there's also the national security focus on cybersecurity, infrastructure security, and things like nuclear weapons, et cetera.
So from Sandia, what did you do?
So Sandia, they actually sent me over here. So Sandia
Back to Austin?
Yeah, they sent me to Austin. So they sent me over here for I was, in a really great program. They sent me over here to do my master's at University of Texas in the computational applied math program. So which probably doesn't mean anything to anybody. Who has a degree in computational applied math? What
Never
the
even heard
hell
of
does
it.
that mean, right? So basically, as I said, what was really lighting me on fire was applying computers to real world problems. I didn't want to just manipulate numbers in a database. I wanted to write code that would help us build things, right? And that's what applied math is all about. It's all about taking kind of the highest end, academic mathematics and then making it apply to the real world. And in particular, a lot of what we do with it is what we term generally as modeling and simulation, right? So that's where we're trying to take a real world problem, represent it inside of a computer, and let it play out so we can do predictive analysis and strength analysis, efficiency analysis, all those kinds of things.
So those are where the biggest muscle of high performance computers were sitting for the longest time, right?
That's right.
The most advanced technologies were probably in those labs, and you were playing with them to try to figure out how to get them to. I think people don't realize how much energy goes into those models and those simulations that take place as well.
Yeah,
right?
human energy and literal.
It literally
power itself. Yeah.
So walk us through what that is like. What's that like?
So, uh, sorry. So nuclear weapons in this country, along with things like NASA, et cetera, those types of programs have really driven a lot of scientific endeavors within this country. And in this case, in modeling and simulation, for instance, once we started signing treaties where we weren't allowed to test weapons anymore, right? Underground or out at Bikini Atoll or any of those places, not allowed to test them anymore. We still wanted to be able to develop them and make sure that they were safe, right? And so the way to do that became to represent those weapons inside of a computer and basically test them virtually.
Theoretical testing
Inside of a computer. And so that drove us to create really big computers and come up with really amazing ways to do modeling and simulation, right? And so a lot of that was driven through programs in the 90s on how to utilize supercomputers basically to do things like represent nuclear weapons, but also look at things like astronomy, star formation, lots of other things that are also related. And then this started to kind of spin out in the late 90s out into a lot of other different areas, especially in engineering and science, and in particular into nuclear energy as well, as far as being able to represent things like a whole nuclear reactor inside of a computer.
No kidding. So how long were you there for at Sandia? And then you came here to get that advanced degree, some master's degree, and some. How
Yeah, yeah.
were you like aligned? Like when I first moved out here in 2004, I was working for a rotary UPS company. Doesn't exist yet. Got bought by. I mean, doesn't exist anymore. Got acquired by Pillar, but they were across the street from the J.J. Pickle Foundation. Have you ever heard of this building?
Yeah, absolutely.
A lot of advanced sciences coming out of there. Were you involved with any pickle programs?
The Pickle Research Campus. So that's where University of Texas has their Advanced Computing Center,
Exactly.
the TAC Center, the Texas Advanced Computing Center.
I've been to that. I'm sure you have too.
Yeah, absolutely. That's also where their research reactor is.
Okay.
You might not know that part.
I did not know that. They
Yeah,
had a reactor with size.
Yeah, it's I can't remember the power on it. I should know. But
Yeah, I got you.
I actually got to go tour it just last year. If you ever get the chance to go look at a research reactor, definitely take the opportunity. It's pretty amazing. Most of the research reactors in the United States now are kind of these fast pulse kind of reactors, so they don't run constantly. You turn them on and they pulse, and then through their own physics, they actually shut themselves down. And the amazing thing is that they're down in the bottom of these pools of water. You can literally stand on top and look down into the pool of water while they pulse the reactor. One of the coolest things, I'll have to show you a video of the one here at Texas. But if you've ever seen photos of a running reactor, it typically has kind of this blue glow around it. For those of you that haven't, definitely go look up these photos because they're amazing, right? Well, that blue glow is something called Cherenkov radiation that happens just because of the interaction of some of the particles coming out.
I would say moisture, probably.
Well, it's slowing down of electrons. We don't need to go into why it happens, but there's this blue glow around any reactor that's operating underwater, and so whenever they pulse the reactor, all the lights go down, and then all of a sudden it's just the brightest blue glow you've ever seen in your entire life, just like whatever 30 feet away underneath water. So it's a pretty incredible experience. So highly recommended.
Well, look, there's a lot. I mean, there's a lot of people that are listening to this podcast right now because they're so. Our data center industry is at an inflection point today, right?
Yeah.
So you and I were talking about this earlier where we're at a point today as consumers where the adoption rate of emerging technology, specifically focused around the surge of AI, has allowed us to discover that the demand growth of AI is untenable and unscalable based on our current energy vehicles. And right now, the whole world is scrambling to find bridging solutions. And like I just spoke at the Permian Basin at a panel yesterday. I flew in this morning from Midland, where we were talking about, I think you live in Northern Virginia. You know that that's the home for the sky for the cloud.
Mm-hmm.
But the home for AI will most likely be in Texas, it seems like right now, because there's so much natural resources, so much available access to fiber, lots of labor force, a lot of land.
A lot of land, yeah.
Right now we're flaring in Midland gigawatts of energy a day,
Mm-hmm.
right? So since transmission of energy is a challenge, it makes a lot of sense to bring the compute requirements and the compute demands closer to the proximity of energy.
Yeah.
Right. So some people don't, I think a lot of people think nuclear and they still have, there's a dichotomy between nuclear weapons.
Yes, absolutely.
And nuclear energy.
Yeah.
Do me a favor, pretend like this is a podcast that kids in college are going to listen to one day and write a paper, and they're going to be like, let me tell you the difference. I mean, fission, fusion, we discovered that 76 years ago, right?
Yeah.
And I don't know what you know on the civilian side, but the nuclear Navy has 30 to 40 different types of nuclear propulsion and power plants today, right? And who knows how many, there could be way more than that, right? And not to mention how many you've seen on the civilian sector. Help some people understand just the basic genesis. People think like nuclear, the element itself creates energy, and I'm like, well, it doesn't work like that. You got to create heat and you create steam, and that's what creates energy. But walk some of those people through that are listening for the first time, because when we're done, I want them to. We have to not deconstruct such a complicated topic, but we have to make it something that's something that all of us are capable of have a basic general understanding of, I mean, the media today speaks at a 7th grade education level. I've done media things like, well, you got to dumb that down. I'm like, this is a topic that you cannot dumb down.
Yeah.
And if you're listening to this podcast, it means you're probably pretty smart. You're in a very sophisticated industry and you're trying to better yourself. So use this as an opportunity for me, Derek, because you got a big old brain. And I mean, first time that we talked, you were rattling off shit. And I'm like, we have to get you on a podcast, right? So what I'd like for you to do is help. I'm going to tie it back into the industry, and you're tracking the industry from AI's perspective.
That's
of compute
right,
demands, and that's where 20 years of your experience comes from.
Yeah.
But start at the beginning for us. So when people walk away from this podcast, I want them to, generally have an understanding, a basic. Right now, I think everyone has a fear of nuclear. They don't have to. It's scary as shit, but that you don't have to be scared.
Fear or curiosity, at least, right? Yeah, absolutely.
But let's try to demystify some of that fear.
Sure. Yeah.
And let's try to make it something that's palatable where people go, you know what, if I lean in a little bit harder, I could probably really get my hands wrapped around this.
Yeah.
Because at some point, I don't believe there's a future that exists in our lifetime where we're not running more on modular reactors of some fashion than what we're doing today. Do you agree?
Yeah, there's no doubt. Absolutely no doubt.
So start at the beginning.
The density of energy that we need really only matches up with nuclear reactors. So we're going to get there. So I think one of the first things to talk about whenever we're talking about nuclear energy is just energy generation in general, right? The way it works in most power plants is that you have some heat source, right? And at a basic level, you generally end up heating up water. That water generates steam. Steam turns turbines. Turbines turn generators. That generates electricity, right? Like I think we got to start there. Like that's our.
But that's a very simple breakdown.
That's our basic breakdown, right? So that heat generation source, that could be burning natural gas, could be burning coal, could be burning oil, right? Or it could be nuclear reactions.
Steam from nuclear reactors.
It could be nuclear reactions, right? And so whenever you're looking at a nuclear power plant, it's really no different than any other power plant out there. It just has a different heat source, really, right? So if we want to dive inside of that heat source, the thing to understand is that, there's many different ways to kind of construct a nuclear reactor. And some of these newer advanced reactors that I'm sure we're going to talk about, some of the small modular reactors have kind of new ways of doing this. But let's talk about the way that it's kind of done right now in the United States with the current fleet. Like if you were driving down the highway and you saw a reactor on the side of the road, how does it operate, right? And the basic way right now is that you have uranium, UO2 generally, uranium dioxide, that is then put into these long, thin fuel pins. Okay, we're talking, a couple meters tall, right? That's another amazing thing about nuclear energy is just how dense it is. I mean, how dense it is. I mean, a nuclear reactor core is really not very large, right? Yeah. And so the fuel is inside of these metal rods, and then what you're doing is that fuel is getting hot. Okay, and we'll talk about why it gets hot in a second, but just believe me for a second that those metal tubes are getting hot, and then you just flow water over them. The water takes the heat away and carries it off, and that's how you get the heat to turn your turbines, etc., right? So again, it just comes down to a fuel source heating up water. Now, why does nuclear fuel get hot? It gets hot because there's nuclear reactions going on. That doesn't explain anything. But uranium, especially certain types of uranium, likes to give off neutrons, right? Which are a part of every atom on the planet, right? And so those neutrons, you could think of them as like tiny little balls, right? It's not always exactly right, but think of it as a tiny little ball. And you've got atoms of uranium hanging around, and every now and again, they just kick one out. They just like punt a ball. Think of like standing up. Let's say you're on a volleyball court or something like that. And you're holding onto a ball. You got a bunch of your friends around you that are also holding onto volleyballs, right? And then all of a sudden, for no reason, just because you don't like his face, you turn around and just smash somebody with a volleyball, right? And what that causes is a chain reaction then. Okay, so that person that got hit by that volleyball is like, you know what? I'm going to do that too. And they take their volleyball and hit somebody else, right? And then maybe somebody's holding a couple of volleyballs, and so they're hitting multiple people, and this thing kind of like propagates, right? And so those volleyballs are the neutrons. They're flying around and running into other atoms, and then those atoms are absorbing those neutrons and breaking apart, and more neutrons are flying out and hitting other atoms. Okay, in the process of this, just like your friend that you hit in the face with the volleyball, stuff is getting hot. Okay, I mean your friend's,
Friction.
yeah, friction. Your friend's not going to be happy, right? He's got, his temperature is going to go up. Same thing for these atoms, right? As they break apart, they're releasing heat. Is the basic plan. And so that heat is released into the larger amount of fuel that's there, and then that heat makes its way out into the metal around the fuel, and then ultimately out into the water. And so, like at a basic level, like that's what's going on. You've got this crazy game of tag or volleyball or dodgeball or however you want to put it, going on, where all the uranium atoms are splitting apart and smashing each other with neutrons, and then that just continues on and carries on.
All right. So for the basic listener that's right now, they're understanding, okay, so there's basically this stick, it's a rod, it's ballistic with energy. It's there's chain reactions taking place all the time, which create this radiation, put it into an element of water. The water it doesn't reject the heat, it absorbs the heat,
Right.
and then carries it onto a turbine. Then that turbine is used to spin to create that transmits energy to a motor generator, which can be used into an AC or DC bus.
Absolutely.
Okay.
Yep.
So now you have this, and there are how many different types of like civilian reactors? And what's the difference between a small modular reactor, a microreactor?
Perfect.
All right. So paint us with a broad stroke. We're all trying to figure out how this market works, because in a little bit of time, everyone that's in this industry is going to be figuring out how does this nuclear impact them as a consumer, as a resident of their community, and then obviously how does this impact their business?
Yeah, absolutely. So right now in the US, the operating reactor fleet, there's only really kind of two main types. There's what we just call pressurized water reactors. All right. And that's
Steam kettles.
you're heating up water that's under high pressure. So it doesn't actually boil itself, right? Think of it like a pressure cooker kind of situation. It's under enough pressure that the water can't boil. So it just gets really hot and carries away the heat. And then that heat is passed off to other water through a heat exchanger.
Yep.
That then does boil and run the turbines.
Okay.
Okay. The other option is that you just boil the water directly. And so that's what we call a boiling water reactor, or BWR. And so the water flows through the core, gets hot enough that it actually boils, turns into steam itself, and then that steam immediately goes and turns a turbine, right? So it's just two slightly different versions of that process. Those are the two types of reactors that we have right now in the United States.
What is the American position today on nuclear reactors versus China?
So right now, China is currently building many, many nuclear reactors.
They've commissioned 10 every year for the last 3 years, with the exception of last year where they did 11, right?
Yeah, I mean, it's tremendous. They have just an absolutely huge program right now. So right now we have more operating reactors than China, but as soon as they're finished building the reactors that they're currently working on, they're going to catch us and surpass us very, very quickly. And they're building some of these kind of traditional designs, but they're also building some of these newer advanced reactors as well.
Are they have their own designs on these? Or are they using Japanese designs, Korean designs?
Actually, some of them are American designs. So, or were licensed from companies here in the United States, for instance, Westinghouse.
Interesting. So Westinghouse licensed reactors to China so they could overtake us in energy.
Yeah,
You didn't say it like that.
I'm probably not going to want to touch that one.
But my thing is this, is a lot of these great technologies come from America, and we're being outpaced right now by China as an example on energy. Energy is the most critical. There are the two existential threats to the data center space are energy and people, right?
Yeah.
And right now we're trying to deconstruct this thing on energy. How many types of nuclear reactors does America have right now? And then think about this. 3 Mile Island, Fukushima, like Fukushima, like what are some of the battles that you've had to see? Because you're out here pioneering and advocating for nuclear, right?
Yeah, absolutely. So The history of nuclear energy, again, it goes back to the weapons first, but very quickly, very, very quickly, we came up with atoms for peace, which was trying to harness all this energy for.
Didn't Oppenheimer have something to do with the origination of Department of Energy with regards to nuclear reactors?
So Oppenheimer was, part of the Manhattan Project and part of standing up the National Laboratory system. But there were a lot of people involved with coming up with atoms for peace, for instance. But Dwight Eisenhower, was the one that kind of ultimately gave the speech to the United Nations.
I do remember that speech. Yes. Back then they were predicting that our entire electrical grid system by then would be on nuclear.
Yeah, absolutely. I mean, it was really viewed as a futuristic technology that was going to just make energy availability
to everybody,
just absolutely abundant and
economically efficient too, like clean, renewable, reliable, safe, scalable energy for everyone.
And so we built a whole bunch, right? We've got nearly 100 operating reactors still in the United States, even though we haven't built very many for the last
20 years,
30, 40 years, actually.
Okay.
And so that's because we built a whole bunch immediately because it was such a great idea. But then things came along, right? So first of all, because of kind of this link to weapons, and going through the world's buildup of nuclear weapons and what that meant for humanity, these things kind of got mixed up together a little bit, right, in people's mind's eye. And then we had events such as Chernobyl, for instance, that happened, 3 Mile Island, later on in kind of our more modern times, Fukushima, right, that have also just not helped as far as public perception of nuclear energy.
Do you have anything to say about those in contrast to what the perception is in reality?
Yeah, so I could go through each one. So Chernobyl, for instance, was a fairly poor design, first of all, as far as its actual mechanical design. As soon as something was going wrong, it was really difficult to correct it. Plus, there was human error and some instrument error as well, right? But it was a Russian reactor, a Russian design that had, some engineering issues that we wouldn't allow at all today, as far as physically how the machine worked. And then 3 Mile Island was, again, a human kind of error situation along with instrument error. So there was...
it was primary coolant leak. It didn't get to the secondary side, right? I mean, the safety parameters... Go ahead.
The safety kicked in, but the human operators couldn't understand the condition of the reactor because of kind of some limited information in their instrument panel, right?
Okay.
And again, it's just things that wouldn't happen today, like literally not possible, because we have so much more information about what's going on inside of a reactor than we did back in the day. But basically, there was a valve that they couldn't understand the state of, and so they ended up taking action in kind of the wrong direction. Now, one thing about 3 Mile Island that a lot of people don't know, but is really relevant to today's discussion on data centers, is that there's another reactor on 3 Mile Island, right? There's Unit 1 that operated perfectly safely for many, many years. I don't remember how many years now, 40 years, 50 years, something like. And that is the unit. It got shut down a few years ago. And then now...
is it Microsoft?
Microsoft is... working to turn that reactor back on to power some of its data center ventures in the Northeast. And so even as bad as 3 Mile Island was, there wasn't a huge release of radiation, that sort of thing. It was really fairly controlled, but it did render that reactor non-operational. But the other reactor that they built on that site had a perfect operating record through all the rest of the time it was operating, and so good, in fact, that now we're turning back to it to turn it on again. And then Fukushima is probably one of the more unfortunate ones.
More design problems.
This was again a design problem. You've got a backup diesel generating
below the sea level.
That I don't think it was below sea level, but it was not high enough above sea level that it wasn't escaping from the huge wave that
they just got flooded.
inundated.
They couldn't cool the system.
It got flooded. The primary electricity coming into the plant got turned off, which is when you would want the backup generator to come on to keep that water. Really what it does, going back to how the reactor works, you got to keep that water circulating to keep that fuel
stable.
Well, cooled, honestly. The real problem is not radiation, it's heat. And if you're not circulating that water, you're not getting the heat out of the fuel, and then the fuel is going to melt itself, literally melt through the metal and melt itself. And so that's what ultimately happened at Fukushima. It was just the backup generator was in the wrong spot. They had spec'd it for the size waves that they expected, and the wave was just bigger.
The tsunami, yeah.
It was just bigger.
All right, so we have a history, though, worldwide, not America. I mean, all the rules and regulations to air traffic, like when we redefine what the rules will be around, it's all written in red, they say, right? It's written on disasters. So maybe we shouldn't design it like that. Maybe we can't make it to where you can't access it if there's an emergency. Maybe we shouldn't make it to where we have these cheaper gauges where we can't analyze and interpret what's really happening in real time, or we need a backup plan for that in case that happens. But I do think that we've never been in a safer time to operate and run nuclear reactors. I think a lot of people feel like it's still so new. In reality, it's been around for a long time. It's very proven.
It's very, very proven with a very good track record, right? We're talking about 3 instances throughout hundreds of reactors operating constantly throughout the world, right? And so,
how many people were accredited? How many deaths were accredited to Fukushima?
I honestly don't.
I don't think it's a lot.
No.
I mean, according to some places, it's 0. Yeah. Right? I don't know about 3 Mile Island having issues with humans. Obviously, Russia's a completely different one.
I don't think there was anything attributed to 3 Mile Island, as far as I know.
I feel like the perception of what nuclear is, you have NIMBY, right? You have every one of us is a member of NIMBY, right?
Yeah,
not in my backyard, not over there either. Yeah. And we have to break and shift the way that people perceive it. I'm like, I want to find the right words. I want to find the right people that can put together the right keywords and tricky phrases that allow people to take the binoculars that they're looking at nuclear through and flip them the other direction.
Absolutely.
And what are you seeing? You're seeing lots of problems, or go ahead, lots of challenges.
Yeah. So I think part of that is understanding the new technology, right? The other thing about Fukushima is it was very old design, and we don't design them like that anymore with a backup generator that's buried under the ground, like that sort of thing. You just don't do that anymore, right? And so even in kind of traditional nuclear reactors, there's been a lot of upgrades over the years to make them safer. But what we're looking at now is an all new set of advanced nuclear energy technologies. And as you mentioned kind of earlier, the United States really is, one of the things that's amazing about this country is how much of an innovation engine it is, right? And one of the things that we've been pioneering is a lot of these new advanced reactor capabilities, right? And so even for kind of more traditional looking reactors, like the light water reactors we talked about just a little bit ago, we now have safety systems that, for instance, don't require any electricity to run, right? They'll be like gravity-fed systems where you'll have tanks of water that are above the reactor that can flow water or flood the reactor, that sort of thing, no matter what happens. And multiple layers of kind of like fail-safe safety systems on top of them, right? So even a traditional reactor today is, in a much better place than what was in the past. Because we've learned from our lessons, right? So
let me paint with a stroke there for those that are listening. I always say that what 2025 is for AI is what 1925 was for the automobile industry. So if you think about that, how new is the automobile industry as a whole by 1925, and how thriving was it to society and to the communities you lived in? How exciting was it back then? And now if you look at those cars in 1925, you would never operate even the phones that we use,
Yeah.
And the first iteration of everything that we ever use, it's exciting, but it always tends to be the worst. And right now we're functioning with AI models, AI technologies, although they've been around for a bit, they're still the worst, right? I mean, AI will only get better
Oh,
every
absolutely.
year.
Yeah.
The stuff that we're using today, it'll just be that much better in a year from now, right?
Absolutely, and it's really accelerating at a pace that's truly unbelievable. And that's true of nuclear energy as well. I love the automobile example that you just gave because when were seatbelts required?
Right.
Why, like in the late 70s or
80s?
something?
Yeah.
Was it all the
No,
way
I
into
had
the
a mom that
80s?
would just do this. The mom had the
Yeah,
arm that would just cover you. Did you have one of
exactly,
those?
exactly. And I think that's a really great comparison that we don't always necessarily engineer perfect safety
Right.
the first time around. But nuclear energy has continued to advance and get safer. And so, we've been teasing. We said the word advanced reactor like multiple times here, but we haven't talked about what it is. So I
What
think
is it,
we got
Mark?
to get into that a little bit. So there's new reactor designs, for instance, that either utilize water and they're smaller designs with a lot of built-in safety systems. Those are what we call Gen 3 plus. Okay, so when you're looking at different generations of reactors, there's like first gen, second gen. And where we're at right now, we have Gen 3 plus reactors. So those are smaller water-driven reactors that
What's
are
small? Less than 200, less than 500, less than what are we talking?
generally less than 300 megawatts. Okay, where kind of the bigger reactors today, just for the audience, our normal reactor size is between like 800 megawatts to like 1200 megawatts, like 1.2 gigawatts, somewhere in there, right? Um, and so we have smaller systems with a bunch of safety built into them. Those are Gen 3 plus. And then we've got what are called Gen 4 reactors, which generally are not utilizing water for removing the heat from the core. They're utilizing other things like molten salt, for instance, and liquid sodium and
Really?
molten lead and lots of other things, right? And there's a lot of reasons for that, and a lot of it goes back to safety, and then the other thing that it goes back to is
Weight?
size.
Oh,
Size, and that impacts waste as well, right? So with some of these other materials that have higher heat capacities, and better thermal conductivity, you can remove more heat from the core, which means that you can make the energy density even higher within a core, and that means you can make the whole reactor
bigger.
smaller.
Oh.
Smaller. For the same power output, you can make the whole reactor
Oh, I got
smaller,
you, I got you.
right?
So, the same thing we're doing in data centers. We're building bigger data centers, but the densities are getting smaller, are bigger because the footprints are getting smaller.
Yeah, that's right. Yeah, as you plug more NVIDIA cards into the same cabinet, you're using a lot more electricity, and that's the same thing that's going on the nuclear side. Again, kind of that parity between what's going on in data centers and nuclear. In the nuclear world, we're kind of shrinking and densifying the energy generation by moving on to newer different technologies for moving the heat through the system, and somewhat based on how our fuel configurations are too. It's not necessarily fuel rods anymore, it's other things.
Really?
Yeah,
So
absolutely.
what's the most prevalent right now? Gen 3 plus or Gen 4s?
Prevalent in the US, we're trying to get
Gen
all of them.
2s?
No, we're trying to build all of them. It's an all of the above type of situation, right? Just like Chris Wright, Secretary of Energy Wright, has said here in the United States that he wants an all of the above energy policy that really, is pushing our energy dominance here in the US. We've in our microcosm of nuclear energy, the same thing. Every reactor, any reactor is a good reactor. So
What's the biggest pushback right now on regulatory issues? Why are we not getting more of these things built? Knowing from a national security perspective, China is publicly stated that they want to surpass America in our dominance of AI by the end of 2030.
Mm.
And really, based on the trajectory they have on energy, it's not impossible for them to do that. Do you agree?
Yeah, I mean, energy is going to be critical to expanded AI rollout and continued acceleration of AI innovation. We're not going to be able to do it if we don't have the energy that's needed to run the data centers. There's no doubt. And whatever economy comes out with the largest, most stable, resilient energy system is ultimately going to be set up the best for kind of going into the next, digital revolution of, AI everything,
Digital, yep.
basically. Yeah.
All right, so what's the story? How come we're not building more reactors?
Well,
Why are you holding us back, Tim?
well, part of it is that many of these technologies actually are new, and we're actually literally still working on the designs.
So why aren't we building the ones that aren't new? We've had nuclear reactors for 70 plus years, almost 80 now. So why aren't we just doing more of the ones that we have so much history on that we could prove and demonstrate these are safe, right? So how come, what is it? Is it the public opinion that's holding us back?
So public opinion has been an issue in the past. Um, I would say that public sentiment has been changing quite a lot over the last 10 years. And we're getting more public buy-in on, this clean resource for generating baseload energy. But anytime you're putting in a nuclear reactor, you still have to go into that community and educate that community and make sure that they're okay with what you're doing and that everybody's on board, everybody's moving forward. So that takes some amount of time. But right now, the last two reactors that we built in the United States were at Plant Vogtle down in Georgia. They were Westinghouse designs. We were mostly building them kind of during the entire COVID situation. There was a lot of things that happened there. And we learned a lot as we built those because we hadn't built that type of a reactor in a long time. And it turned out to be pretty expensive.
How much, I was just going to ask you, we know what it costs to build a megawatt for Bitcoin mining, for data center providers. What is the cost of a megawatt for a nuclear reactor?
I don't think we know.
If you're doing 300 megs
right now,
so are we in the billions? Because that's a fuel source that lasts 20 plus years, right? So
actually more like 80 years, right? So our current operating fleet is at 60 years. They're getting pushed out to 80 years. So yeah,
really?
It's one of the great things about nuclear energy and why it matches up with data centers is because once you create this generation source, you have that energy for
you're locked
long.
up. That's right now. Energy is as long as pulling the tent. Man, I'm all over the place because I'm so fascinated with this topic. But,
no, I know, me too. So how much does it cost? We don't 100% know. So the Department of Energy Loan Program Office has put out a study called the Liftoff Report that goes into detail about how much various scenarios would cost to build out, right? And the main thing that we know is that when we're building these, what we call first of a kind reactors, the very first one of a new technology, it's going to be expensive because you have to learn things as you go.
The first time you do anything is always the most expensive.
Exactly. And so that's going to be the case for these first nuclear reactors as well. And then there's a learning curve associated with that, right? And once you build one, you learn things. Once you build 2, 3, 4, you learn things, and it gets cheaper and cheaper, right? And so ultimately, the price of nuclear energy, as shown in the Liftoff Report, is on par with other energy generation sources. But there's no doubt about it that some of these first reactors are going to be expensive.
What is the greatest pushback? And I keep asking that, and I was waiting to draw you out in hopes that you'd say oil and gas. Oil and gas is probably the groups that make the most, they have the most to lose from us shifting away from fossil fuels into a nuclear model, right? I mean, who has the most to benefit and who has the most to lose?
Yeah, I don't necessarily think that because, again, going back to Secretary Wright and his all of above energy strategy, there's places where natural gas, for instance, is going to make a lot of sense for a long time to come.
Yeah.
And there's places where nuclear reactors, especially some of these smaller, more advanced designs, are going to be able to come in and serve niche capabilities that you wouldn't even be able to do with natural gas. And the two things are not opposed to each other either. So if you look at Oklo, for instance, which is one of the nuclear reactor technology startups, they have partnerships with several data center companies, but they also have a partnership with a company called R-Power to build natural gas generation capabilities as well, which is really interesting, right? So you're talking about a nuclear reactor company, but they also are looking to build natural gas generation sources. And why? It's so that you can do things like start a data center project up and build natural gas to kind of help get it off the ground while you're building nuclear
That's
next to
exactly
it,
what the plan should
right?
be. Yeah.
Yeah. And so this is not an either or, it's a both, right? And then ultimately, as time goes on, you end up with both types of generation on site or near that data center, and you can use them for different parts of your operation, right? Depending on what your load profile looks like on the computer, or what your interaction is with the grid. Maybe you use, for instance, the natural gas for doing peak shaving, so you can shave off some of the pull that you have on the grid during peak hours, that sort of thing. Maybe that would help you get your grid interconnection faster, for instance, by having some sort of peak shaving agreement with the utility. So there's lots of reasons to actually build both of these things. They're both going to have their purposes.
I spoke at a summit, like I said yesterday, where one of the guys got up and said there's 100 gigs of interconnection requests just in the state of Texas alone
It's incredible.
between now and the end of 2027.
Absolutely.
It's incredible, right? But like a lot of those, where is the most ideal market for a reactor? I mean, obviously the oceans seem to be close to where we build most of them, or right on the beach line. I would imagine if you look at like a map of the United States, you have the reason why reactors are interesting to talk about is it's almost a political thing, right? It is to some people.
I will cut in and just say that we've had really great bipartisan support from Congress for the last many years, and that's one of the reasons why we're in the position that we're at now to be able to deploy these technologies. So at that end of the political scale, I'll say that it's a bipartisan effort at this point to get these technologies deployed. But yeah, there are certainly different camps in the United States of people that say one thing or another are on different sides of the nuclear energy spectrum, right? So
I feel like it's the camps that have been fed more propaganda than the other. Some people objectively are going to ask questions and try to understand it, and some people are just going to believe a lot of the things that they hear that are fearful regarding nuclear reactors, right? And we don't really have a lot of evidence to point towards that says that these things will destroy our country or destroy our nation or destroy things. But what I was saying about the political side is there's a lot of the nicest places in the United States along the beach lines tend to be they're more blue than red, right? So I'm like, are there parts of the country where they're more welcoming to reactors than others, you know?
yeah, that's absolutely true, but even that is changing. So for instance, right now there's a moratorium on building new nuclear in Oregon, for instance.
Why is
right?
that?
It's just a long-standing policy of theirs.
Political driven, probably, right?
I don't know. Is it driven by just the outlook of Oregonians, I suppose, right?
Yeah.
I don't actually know exactly how that particular policy came about. But what I can say is that there's already discussion going on in Oregon about whether they want to continue that,
The
right?
moratorium or open it up because it may be
And we've had
safer.
several other states. For instance, Illinois has recently undone their moratorium, and New York State has changed their stance on the build out
How recently was
of
that?
new, just even within the last few years, right? So these things are changing right now.
So people are
as
shifting.
Yeah, as the need for energy changes, it becomes more and more obvious that nuclear is the right answer. And so we're getting a lot of public sentiment change, and we're getting a lot of policy change at the same time.
So what do we have? What's it like? Tell the people like what's out there right now. We have more reactors than they probably assume, but there's typically only a couple different types. We're rolling out new prototypes of 3+.
Yeah,
of
that's
course.
right.
But there's no moratorium federally on these things. So
No.
do we have any nuclear programs going on right now in the United States that are building reactors right now?
Yeah, absolutely. So, and this goes back to the national laboratories. So the national labs have long played a role in nuclear energy, and they're playing a really important role again in helping these nuclear reactor startup companies, these companies that are pioneering these new types of nuclear reactors, helping them build those first of a kind reactors so that we can, go through the design phase, prove that they're safe, get over some of those first of a kind kinds of issues, right? So Idaho National Laboratory, for instance, has the National Reactor Innovation Center.
Is that where Brian went to go work at?
Yeah. Well, I don't think he went to work for NREC, but he went to
Okay.
work for Idaho National Lab, right?
Okay.
And they're that's where we're specifically working with companies such as Radiant, Westinghouse, Oklo, and others to build first-of-a-kind reactors at the national laboratory so that we can test them and help those companies build, have a place to build those, basically. Other reactors are going in down near Oak Ridge National Laboratory, for instance. Kairos is putting in reactors there. They have a reactor called Hermes that's going in down there.
How long does it take to build a nuclear reactor? Is that what size is that, by the way? Is it 300 plus or something?
So most of these demonstration reactors aren't generating much electricity. It's really more about
Okay.
showing that the technologies work and that
Got
the
it.
designs are proving out.
So a lot of these advanced energy creators are at the labs only, you're saying? They're not commercialized just yet and rolled out to...
Right. So these are commercial companies, but the federal government's offering opportunities for them to build and accelerate builds of these first-of-a-kind technologies, right? And one of the programs at the federal level that is doing that is a program called the Advanced Reactor Deployment Program, or ARDP. This is where we've put a lot of government funds into many different projects, but two of the premier projects, one from TerraPower and one from X Energy, to build two small modular reactors in the United States. So the one with X Energy is working with Dow Chemical to generate not electricity, but to generate heat to drive chemical processes, right?
Really?
So these new reactors have there's some new ways to use them other than just generating electricity. So whenever they're denser, they can generate higher temperatures, and that the heat that comes out of the reactor can be used then to drive chemical processes directly, right? So that's one thing that's going on. And then TerraPower is building out in Kemmerer, Wyoming, in western Wyoming, another plant out there on this ARDP project as well. So the federal government is putting funds and making land available and sites available for these new reactor technology companies.
What are some of the things that you're seeing as a trend on the Department of Energy side?
So I think a trend is towards, well, first of all, I think we're all guided by the executive orders of the current administration. I think with everything that's gone on in the last couple of months as the new administration has come in, there's been a lot of executive orders, especially around energy. And so we're really driven to carry out what's in those executive orders to, as those orders specify, unleash energy dominance in the United States, right? So the entire Department of Energy is really focused on that. But in particular, in the nuclear area, Secretary Wright has made it clear that he wants to make commercial deployment of nuclear reactors a priority, right?
Interesting.
And so we are working directly with data center vendors and nuclear reactor companies and trying to find novel pathways, new funding pathways for getting new nuclear builds put together. At the same time, we're looking at what else can we do as a federal government to help and accelerate things. Things like in the executive orders, one of them spells out that we should be utilizing more federal land for these kinds of activities. So are there places in the U.S. where we could provide federal land to help build commercial nuclear reactors, for instance, is something we're looking at. We're definitely looking at all the processes within the government that involve the speed at which we can deploy a nuclear reactor and trying to streamline things, trying to make intergovernmental work groups and things like that in order to speed up or accelerate the delivery of
China's got
nuclear.
$500 billion going into reactors right now. That's why I'm like, it's a lot of money,
Right.
but they take a long time. How long does it take to build one of these reactors?
It really depends on the size, and that's where we're hoping to innovate with some of these newer reactor designs, right? So a traditional reactor could take 10 years to build, for instance, right? Which is a long time, especially when we're talking AI, right? But some of these newer designs that are smaller, the smallness actually helps us out in a lot of different ways. And one of them is that we can do things like prefab, just like a prefab house or something like that, right? Where we can do a lot of the fabrication in a facility and then truck the pieces out to where they need to be installed and then install them very quickly so that we don't have a lot of on-site construction processes. That can speed everything up, and it also makes everything, it reduces the cost of everything as well, right? But some companies, such as Allo Atomics, that's based right here in Austin, Texas, in fact, they're looking at things like manufactured nuclear reactors. So this is where you're going to have a literal assembly line
Yeah.
that is having full nuclear reactors rolling off the end of the assembly line, right? And then you just drive them to wherever you want and put them down and plug them in, kind of thing, right?
So the types of reactors you were talking about first, because there's different types and different sizes,
Yeah,
right?
that's right.
So you're talking about ones that are more used to replace current existing power generation plants, and they'd be serving as a a part of the framework of the foundation of the utility. These ones that you're talking about are smaller ones that would probably be used in residential applications. Is that about right?
So residential applications, maybe, residential applications tend to be kind of well served by the larger, more efficient, like
Utility
utility type,
versus not
utility
just one
scale.
that serves that neighborhood type of thing.
Yeah, that's right. That's right. So yes, smaller reactors such as microreactors, which are typically kind of under 20 megawatts. Um,
Are those the ones that you're talking about for manufacturing, like an automobile? That's what I was
yeah,
envisioning.
exactly. Yeah, because they're the size is critical to
That's
being.
like a submarine type, a little bit. We're a little bit bigger on a sub, but I mean, not.
Yeah.
I mean, the thing is they're not that big, right? So you
Right.
could put it somewhere and people wouldn't even know that that's a reactor.
Yeah, absolutely. So, um,
Yeah, go for it. You're in Austin. It's been back. It's the allergies of
yeah.
Austin. You don't like that cedar? You didn't hear me.
Sorry.
You didn't hear me sneezing at lunchtime about 1,000 times.
I know.
You're fine.
All right, I'm gonna get there. All right, we're good now. So, the size of the reactor really impacts the way that you build it, right? The biggest reactors, such as the gigawatt scale reactors, you really have to do a lot of construction on site, and that's kind of more expensive. It's more bespoke as far as you have to kind of engineer things for that site, right? But as you go smaller, you get to more kind of
Modularized, standardized.
modularity, repeatability, iteration building kind of activities, right? So 300 megawatts and under, you've got the small modular reactors, such as some of those Gen 3 plus ones that I mentioned earlier. And then under 20 megawatts, we've got a bunch of micro reactors. And this goes back to asking about, how does natural gas versus nuclear reactors or coal versus nuclear reactors play into each other? Well, there are going to be use cases for like a 15-watt microreactor where you would never put like a full natural gas plant, right? But a 15-watt microreactor can get placed, let's say, next to a piece of critical infrastructure somewhere, and power just that piece of critical infrastructure, where you wouldn't really want to do that with like a natural gas plant or something like that, right? So there's going to be different uses for these. One of the uses that we're seeing for microreactors, the Department of Defense is very interested in microreactors. They've had a project called Project Pele going for quite a while now on development of kind of a mobile microreactor that could be forward deployable, for instance, right, for powering bases and critical infrastructure. The Department of Defense, in particular, the U.S. Army, in concert with the Defense Innovation Unit, has recently put out a request to look at microreactors for powering critical infrastructure on domestic bases, for instance, right? So we're going to see some of these kind of niche.
Are those designed to not really need someone to be? They don't need a Homer Simpson sitting at a reactor control panel watching it 24/7, 365. Like those larger ones do, right?
Right.
The smaller ones, the micro ones, are they designed to just sit down and plug in and they're self-contained?
Well, I think that brings us back to AI. So we haven't talked a ton about AI and data centers, right? But one of the things I like to say about AI and nuclear energy is that they have effectively a symbiotic relationship, right? So you've got AI that needs a tremendous amount of electricity, where nuclear energy makes a lot of sense. It's always on, is reliable. It can run for a long time without interruption. Some of these newer designs are spec to run out to 10 years without interruption, right? which is absolutely incredible when you're talking about downtime on a large AI data center. Um, and then on the other end of that, though, we've got AI for nuclear, right? Which is utilization of artificial intelligence for um, optimizing nuclear reactors and accelerating their deployment, right? And whenever you talk about control, for instance, one of the things we're working on is autonomous control for some of these smallish reactors, which means having an AI based system. Maybe it still has human in the loop on
But it's
making,
fully automated, right?
but
Yeah.
a large amount of that operation can be done in an automated fashion using AI. So that's just one of the places where AI can be useful for nuclear energy. But we're going to see this continue where nuclear energy is going to drive the ability to build bigger AI data centers. And AI is going to continue to drive
The
the
ability
the
to do that.
design and deployment of nuclear energy.
I I agree. They are symbiotic. What are you? You're seeing today data center. Are they owner operators, right? So a lot of people don't
Yeah.
realize that the world for data centers is like the world of a grocery store, right? You have a
Mm,
wholesale like a Costco, you have your local grocery store you go to once a week, and then you got
yeah.
convenience stores, right? And the data centers are kind of built like that. We have carrier hotels or convenience stores that are in all the NFL cities that connect the hub and spoke fiber backbone of the whole world internet, so to speak.
Yeah.
And then we go and we tether off of those into outside the NFL markets into the suburbs and stuff, and we build these large wholesale facilities all around it. Um, the product that we used to build in a data center used to just be four walls, a roof, some space, some power, some cooling, and we would sell it on. I mean, the interesting thing about technology and our real estate perspective is it's sold in a price per kW, right? So we only sell power in data centers. We don't sell real estate, as an
Right.
example. So I could see the product evolving to where for every, let's say we standardize on a 100 megawatt reactor and we
Right.
marry that to a 100 megawatt hyperscale data center. We know that, that accounts for X amount of gallons of water used a day and X amount of gallons of water per acre. We could probably even quantify it down to how many acres is necessary.
Right.
Like, do you have that? Like, I know that there's 30 acres of land for one wind farm megawatt,
Hmm.
5 acres of land for one solar megawatt, right? So there's certain real estate topologies. I know a 100 megawatt data center is at least 40 acres, right? But the larger you go, the better, especially if we're putting an on-site power generation plant of some kind, whether it's nuclear or natural gas.
Right.
How much power, I mean, how much available real estate do you need for these reactors?
Yeah, I think that's one of the other reasons why nuclear is going to end up being a really great solution
The footprint is so
for
small.
data centers, is because the energy density and the footprint is so small, right? Even if you have a much larger reactor like the Westinghouse AP1000 plants that we built at Vogtle in Georgia, where they have a fairly large, what we call exclusion zone around them, like 20 miles or something like that, right?
Yeah.
Where we don't have
The
a lot of
offsets.
where we don't have a lot of economic activity in that area. Um, we we are still building at some of the nuclear reactors like that. We are still building data centers close to the nuclear reactor as well, right?
Like the Talon one
Within,
in
yeah, like the
Pennsylvania.
Talon one in Pennsylvania, exactly. So even in the case where the entire boundary of the nuclear reactor generation capability might look fairly large, that's also a lot of room where we could build data centers as well. But again, that's kind of the traditional nuclear reactor gigawatt scale. When we look at some of these smaller ones, we're going to see that exclusion zone go all the way down to just being the size of the building that the reactor is
Yeah.
in,
That makes
because they're so small, and the consequences of these small reactors with a small amount of fuel is so low that the exclusion zone is just absolutely tiny. So the nuclear reactors to run some of these data centers will absolutely be smaller than the data centers themselves.
And I see that those ones that were pairing reactors with data centers on, because I'm involved in a lot of different conversations
Yeah.
right now. A lot of uh, people that own land in Texas have retained us to go out and do data center site feasibility studies on their land to determine how to help them make a business case to justify deploying capital into developing a data center. And the biggest thing that we used to look at was fiber and, all the basic stuff, flood zones, all those things. But
Right.
and these operators right now are pretty sophisticated. They have their own procurement teams that are armed to the teeth, and they know how to negotiate their own PPAs with a local utilities. But
Yeah.
in this case, we're going to be building data centers with power plants that will probably never go into a grid connection request, or they're 4 to 7 years out, right? Because
Right.
they're there just to generate power for one product, right? And that is enough to support that one data center.
Yeah. I think we're going to see a plethora of different options. You've got in front of the meter options as far as like Microsoft is doing with the Crane Clean Energy Center, which is where 3 Mile Island used to be, right? That's
I
going
thought that got shut down. Is that going to turn back on?
um well, that's the
Amazon tried to buy Talon. I thought it was shut down. I thought Microsoft and Google were going to try to do the 3 Mile Island one, and I got shut down too. It doesn't mean they're not going to go forward. It's just it rocks back and forth. Those are really complicated
you know,
deals.
the 3 Mile Island one is just progressing. It hasn't
It
had
is.
any issue. It's ahead of schedule. In fact, I just saw
Okay.
this week that they were saying it's ahead of schedule. There's the Talon situation with Amazon, where Amazon is able to take some offtake from them under their current agreement, and then they're still working on getting more offtake, and that's going back and forth. There's things to work out there, but the Microsoft Constellation deal with 3 Mile Island, or what's now the Crane Clean Energy Center, is a in front of the meter situation. So all the electricity is going to go onto the grid, and then Microsoft's just going to offtake from the grid somewhere else in the area. So we're going to continue to see that type of operation, and then there's the other option is kind of behind the meter, which means the data center itself is located kind of off the grid and more directly connected to the generating source itself. And so there's going to be agreements on all different sides of this going forward.
All right. So look, this is a 2-hour podcast, a lot to unpackage in this thing, and I'm
Yeah.
trying to take it in phases.
Yeah.
All right. So we talked about who you were and your basic. I always interrupt someone in the middle of their part because we got you to your time at UT.
Yeah.
And then we just jumped into reactors. I didn't get to how you got a big fat brain of math and how that got you into. You started in the HPC environment from an energy perspective, and that's what led you into AI environments, correct?
Yeah. Yeah, absolutely. So my background, I started just wanting to play with the biggest computers, as I mentioned, right? I mean, that was the dream. Can you imagine? I mean, I was 20 years old. I get to go program the biggest computer in the world to do something cool. I mean, that was incredible,
Yeah.
right? So that naturally led me down a line of, again, wanting to apply these huge computers, but make an impact on the real world, right? And I had a friend that went up to Idaho National Laboratory, which is our nation's nuclear energy laboratory. And he went up there to work on nuclear energy. And I thought, you know what, that's a really cool application. I would really love to have some impact there, right? Plus, there's some other benefits like skiing and mountains and some
Idaho's
other things.
beautiful. I was born there.
It's
Yeah.
it's a absolutely beautiful part of the world. And so I told my friend, like, hey, if there's a spot up there, let me know, right? And so he called me up a few months later. He's like, hey, there's a spot up here. I think you could come up here. We've got basically a green field, which means, they're starting a program from scratch effectively to do modeling and simulation of nuclear reactors. So I went up there, interviewed, and they were like, you know what? You can come up here and start your own program and grow it from scratch, right? I was 25 at the time. Absolutely incredible opportunity. So I jumped at it, moved.
They didn't need you to have a nuclear accreditation or certification or experience of some kind. They
No,
just need you to understand how to do the math.
Exactly. I had no nuclear background at all. But it turned out that was actually a benefit in a way, because I kind of came in with an outside perspective.
No
right?
limits and construct.
Exactly.
Yeah.
So I came in and looked at the problem in a new way and created this platform that allowed us to build these really, really advanced modeling and simulation tools for nuclear reactors that are now getting used by these startup companies around the United States and by the Nuclear Regulatory Commission to actually make sure that all these designs are safe, efficient, to optimize them, all those sorts of things, right? So coming in with that kind of math and computer science background allowed me to have a different kind of impact on the nuclear community. Now, eventually, even Idaho National Lab got tired of me not having a nuclear background. They sent me off to MIT to do my Ph.D. in computational nuclear engineering. So eventually, I did go get that nuclear training that I really needed. But having that perspective of coming from good software development background really, enabled me to have a big impact. And, that's something I've carried through my whole work is try to have an outside perspective on what you're working on, try to look at it from different angles, right? And so I carry that all the way through into the Department of Energy now, where a lot of the work that I'm doing is w- just finding novel solutions for getting new nuclear built, right? So we've
Yeah.
talked some about data centers, but there's lots of other opportunities too. I've worked on things like chip fabrication, for instance, nuclear power powering some of the nation's new chip fabrication facilities
Behind the meter,
behind the meter or in front of the meter, but just in general. It matches up very well there because again, they need really
massive
reliable,
volumes.
very reliable, right? If they get even a
Their
small dip,
PLCs trip offline. That's millions of dollars of lost.
millions of dollars. Another industry where you see millions of dollars of loss for a small loss of electricity is aluminum smelting, for instance,
Oh, wow.
right? So you've got some of these kind of like heavy industries. In aluminum smelting, I think the time is like 2 hours or something like that. If they go down, if their electricity goes down for 2 hours, they lose like the whole facility.
Oh, wow.
It all just like freezes in place effectively.
Really?
And it's millions and millions of dollars to get it restarted. So there's all these places in the United States where you need a lot of very reliable, resilient electricity, where nuclear energy really makes a lot of sense. And so we have all these new designs, new reactors that are just ready to go right now at a time where we also have a lot of need
Yeah.
for them. And so those two things are really matching up.
Who's the number one advocate for these nuclear reactors? Is it Secretary Smith, is what you're calling him, a Department of Energy guy? That I guess.
Secretary Wright. Yeah.
Right. I'm sorry. So,
Yeah.
and is he big on nuclear, or is he big on balance? And I want more renewables, more of this, more hydrogen,
Uh,
or is he like, hey, someone's going to have to flip the switch for these nuclears?
Yeah, I think the entire administration right now is definitely on board with um, trying to get commercial rollout of nuclear energy. I want to put that commercial word in there because it's an important distinction between the way we do things and the way China operates, right?
Okay.
So one of the reasons why China is building so many nuclear reactors and AI data centers right now is because the government can just say that's what we're doing, right?
Yeah.
And they can put a lot of money into that and just make it happen. In the United States, we have a different system, right? A system that works with the private industry and tries to incentivize the private industry to do various things. And through that system, that's how we get huge amounts of innovation, right? And
Right.
all these new types of designs and reactors and all that sort of
And it
thing.
pencils out typically more when you have innovation with competition.
Exactly, right. We end up ultimately going towards the better designs that ultimately win, right? That's the way our economy operates. So it might operate on kind of a different time frame, but we end up in a better place, right? A different place. And so we're seeing that play out right now in the policies from the federal government, just trying to incentivize nuclear energy in general and let kind of the private markets pick the correct designs to go forward. And that means that as a government, we're not just out there fiating that build this reactor, that one, this one, but we're providing the incentives, the land, we're making the connections between the companies and doing everything that we can to put together these energy generation sources with the need for that electricity, right? And so Secretary Wright's background, he most recently was working at an oil and gas company, but he has a really varied background in just energy generation and energy delivery in general, including being part of the board for Oklo, which is one of the nuclear reactor technology startup companies. So he has a great knowledge across a bunch of different types of energy and understands that no one type of energy is the answer for the country. We really need a diverse set.
But so to those that are listening that are wondering why aren't we having more nuclear? Is it because the technology is scary? Because 3 Mile Island, Fukushima, whatever, or is it because perception is there's your AI, or is perception what's holding things up, or is there technology itself that's not arriving? Like at some point, the soup has to be done cooking. We have to code lock what we're going to use and start
Yeah.
standardizing on those things, right?
That's right. So I would say it's a little bit of both. So first of all, why aren't we building them yet?
Yeah.
is because we definitely had a slowdown in the whole nuclear reactor industry due to public perception.
Yes.
Okay. So throughout the 80s, 90s, early 2000s,
Jane Fonda was out there saying, did you ever watch that movie Nuclear Now?
I haven't seen it, unfortunately.
Dude, with your
I
background,
know.
look, I'm not a
Maybe cut
huge.
that part out.
Well, listen, that guy was Oliver Stone. You don't have to be an Oliver Stone fan, but
Yeah.
you should watch how he brings on, the Sierra Club and Greenpeace and all these people that are
Yeah.
like, look, we were right about almost everything, but we were wrong about nuclear. We have to get on that ship
Yeah.
because it's the only way to reduce the carbon footprint is when we shift to a more it's a safer, more scalable, more reliable form of energy.
Yeah.
And we are using energy at a rate right now where we can look at the linear trending and realize, like, shit, we just don't have enough and we cannot produce enough
Absolutely.
based on the current rate in which we're adopting technology.
The projections are huge now on, the amount of electricity we're going to need over the next 10 years.
So what does the Department of Energy think is going to happen? And I know you can't speak on behalf of the entire department, but what do you think? Is this, if it takes 10 years to build a reactor, is it because 7 years is just the regulatory bullshit that you got to go through to get something greenlit so we could go? Or is it,
So I'm bummed that the only timeline I've given so far in this discussion was the 10-year timeline.
well, whatever it is?
Because it's not going to be 10 years as we
Right.
go along, right? But that's like historically if we look at the bigger reactors. But as we go along, especially once we get over these first of a kind brand new builds, the idea is that it shouldn't take more than a couple of years, to get a
True.
new nuclear reactor build out. If some of these reactor manufacturing companies work out, then it shouldn't take very long at all to truck a reactor out and set it down and plug it in, right? Because the whole thing was built in a factory, and once you get that manufacturing line going, they could be coming off the line every day, every month, or
So
whatever.
we build
right?
data centers like that right now. I build for multiple customers that are building in a modular fashion. Most of everything is built in a static environment where the QA/QC is super high. It also typically gives you access to a much more efficient labor force as well that
Yeah.
pencils out a little bit better. And then we deconflict the conflict with the trades in a field, which
Mhm.
inject traditionally a lot of risk into the programs, which compromise
Mhm.
safety, which is the number one critical path to programs is having to shut down a site because of an
Mhm.
injury or
Yeah.
a safety incident. And most safety incidents happen on a construction site because it's unscheduled, unplanned work, meaning
Right.
somebody shipped the switchgear out there that way, or the busway's coming out the wrong side of the machine and they're trying to fix it in the field, and that's when something happens. But like I can see that we're already the means and methods and how we deliver data centers today has already shifted. In fact, um, there's a guy named Adil in this industry who is the chief technology officer of Compass, and he and I spent a lot of time in the last few weeks talking about how they have really gone through and tried to take a page out of the playbook of the automotive industry to figure out how to manufacture and streamline the modularity, the component and the assemble
Yep.
levels of these things so we could ship them into the field
Mhm.
and put them together twice as fast, right? And it
Absolutely.
sounds like that's the path that the reactor companies are going towards, which lends itself to it's good because we're shifting away from construction and moving more into delivery.
That's right.
And I do think that there will be opportunities for these labor forces, these labor and delivery teams that built data centers to be trained on how to be a part of the delivery team for they're already building power plants. We already build power plants, but doing it on a small modular reactor level that has everything was paid by numbers. It's built by factory. It's component levels. You use some
Absolutely.
specialists.
Absolutely. In fact, I did some work last year talking to several different union groups that are related to build out of data centers and nuclear reactors. In particular, one group that I talked to is a union called SMART, it's a sheet metal workers union. And sheet metal is used all over the place, but definitely used for building data centers, right?
Gen enclosures. We use sheet metal for everything.
All the HVAC, all that sort of stuff, right? That same union has a special part of the union dedicated to building and servicing nuclear reactors as well, right? And so whenever you're looking at workforce development, which we also tremendously need in this country,
Yes.
especially in these kind of like skilled areas, right? Um, is there some pathway where we train a set of workers not only to build data centers, but also to build the nuclear reactors right next to them that are going to power those data centers? And you were talking about the modularity of the data centers, and I think that's an important point that, some of these companies are talking about really big data centers now, right? But you don't go create that data center on day one. Is usually some sort of modular.
It's a campus. We're going to build,
Yeah,
multiple buildings 10 buildings on one campus to
exactly.
get to a gig.
And that's the same thing that we're looking at on nuclear energy, and that's just one other place where there's synergy between these two different things. So as you're building out your data center campus, you can also continually add more modules of
Yeah,
nuclear
that
reactors
makes
next
sense.
to it.
Incrementally just scale it.
And so the two things go together really well. So if you have one workforce that can be used to build data center, stand up nuclear reactor, build data center, stand up nuclear reactor, you can provide a much more stable working environment, long-term employment for those workers, and, grow a really skilled workforce that can make everything better, right? It'll accelerate the rate that you build out the data centers, because that same workforce will be retained over time for building out the energy generation, and it'll drive costs down as well. So.
What else are you like? Okay, so we got you to your PhD at MIT, then you got into all your stuff. You started really studying the impact on energy. This is the part that I wanted to cover next.
Yeah.
Like we were talking in the car, I'm like, I have sat in cool ass meetings, the ones that don't exist, and watched people talking about what they're going to have to do with the rack level as an example to account for the massive spikes that are introduced by these servers every time that you have a prompt into a large language model or an inference data center and you ask this question, and all of a sudden it turns on so much stuff. So you have these swings from 20% idle to a 90% utilization demand or more of energy, and we're seeing how that could be disruptive to I mean, we haven't done it to be able to stand up on an island by itself yet, let alone do an interconnection to any part of the grid.
Absolutely.
So we're in our infancy in this age. And what are you seeing? Because it's no different than what you were seeing on the HPC side before we got to AI. I mean, it's a different level, but it's the same problem, right?
Yeah, absolutely. And I think I relayed to you a story about, uh, I believe at Oak Ridge National Laboratory, whenever they go to turn on some of their supercomputers there, right, some of their high performance computing machinery, they'll actually call
The grid.
the electric company first and give them a heads up. Now, I don't know. I haven't researched exactly what the electric company does in response to that, but at least giving them a heads up that like this big load is getting ready to come back online, right? And so there's obviously going to have to be this interplay between the energy generation and the load in the data
To
center.
absorb those huge spikes, like,
Yeah.
and I said superconductors, supercapacitors, and you said batteries.
Yeah, batteries, some sort of buffering system between them.
I don't-
But another big part of this is something we call load following as well, right? Which is the ability for an energy generation source to basically ramp up and down based on the load that it needs to power, right? And natural gas, for instance, has been good at this over time. It's one of the reasons why we use them as peaking capabilities, because they can spin up really quickly in
Yeah.
order to.
On the recip side or on the turbine side? Recip, probably, right?
Yeah, exactly.
Okay.
And so, um, so some of these newer advanced reactors as well have some of this load following capability too, right? And that's going to help them respond to some of the data center needs too. But like you said, we haven't done this yet. We haven't set up the microgrid yet. There's some research at the national laboratories. For instance, there's a few papers out of Idaho National Laboratory where they simulated a nuclear reactor, and they had a cluster in a tractor trailer effectively that was hooked up to a microgrid in order to start understanding like how are these two things going to interplay, because you have to work out electrically what kind of interconnection do you need between them to make sure that the connection is stable and that load following can happen, and how fast does the energy generation source really have to follow, right? And it's pretty fast. It's pretty fast.
So that's what we were talking about is what happens when we turn on these AI data centers and we start asking all these prompts and it just says, it starts drawing such a massive and rapid influx of demand from this technology
Right.
that just spikes the demand of energy so rapidly, but maybe quickly, just enough to trip something offline, right? So how are we getting around that? And are you working on that side of the energy
Yeah.
problem as well?
So, talking to some of the AI infrastructure providers, I'll say that some of them there's going to be different load profiles depending on what your usage profile looks like, right? So, one cloud provider might be providing AI infrastructure for millions of users, right, that are querying simultaneously and training models simultaneously, and that's going to effectively give them kind of a base level load that's not going to change very much. You'll get some fluctuation just statistically as the jobs move around the various data centers, but then you're going to have kind of these more bespoke data centers that are dedicated only to one company, and are going to be used to train like very particular models.
Yeah.
And I still think it remains to be seen exactly what the load profile looks like, because even at an AI company, take Anthropic or OpenAI or any of those, you've got hundreds of employees that are training models all the time, right? They're training smaller models or parts of models, or they're trying out new algorithms and that sort of thing. And that's using those compute facilities, right? And so it's not usually the case that you just wipe the entire machine off and it's doing nothing, and then you utilize the whole machine, right? But it does happen. So even though it might not be the majority of the time, the majority of the time there might be a nice even hum of activity on these computers. There will be times where the whole machine will be cleared off, and then you're going to start one large training job. And
What does that look like
I
to the
like,
demand of power,
I mean,
demand of
like you
energy?
said, some of these companies are talking about gigawatt scale data centers, right? And so if you're swinging from 100 megawatts of idle electricity all the way up to 900 megawatt load instantly, I mean that's going to take some real electrical engineering to make it all work out, right? So
So the only way to have a stable baseline capability to respond to that would be something like nuclear, probably. But it's just the inrush, the walk-in current is still the problem, right? Is
yeah.
the walk-in is the problem that we're looking at right now.
And I think this is one place where there's a lot of room for innovation. And, every one of these problems that we're talking about, there's a company out there that's looking at that problem and trying to innovate in that space. And I know of some, and I'm sure there are more that I don't know of, that are looking specifically at kind of these microgrid problems of how do we do the interconnection for behind the meter installations, maybe not specifically for nuclear, but just in general, and they'll be able to apply it to nuclear. I think we're going to see things like smart microgrids, for instance, that are working behind the meter, that are using AI to understand what's happening to the load, for instance, and doing predictions on the load and starting up generating resources and things along those lines. Like, again, this symbiotic relationship. We've got to build AI data centers, but the AI is also going to enable us to do things like create autonomous reactors and smart grids and all these other things that can feed power to these bigger AI data centers. So we're going to continue to see that.
We're trying to build these monsters up and feed it enough data so it could teach us what to do next. Is that basically it?
Yeah, absolutely. What as a human race, as a country, all of the above.
Well, that part is scary because a lot of AI was written by humanity, right? And some people just hate humanity, and if you
Mm,
look at some of these markets where people are writing code, not everybody has the best of intentions. So we are seeing, weird things happen with AI as we navigate through AI's teenage adolescence, they say.
yeah.
But we have a long way to go, but we have no choice but to get there because China's competing against us on our dominance of compute capacity. And right now, there's two major reasons why we have that 5-year advance over China. And add to this if you disagree or agree. One is we started making mainframes technically in the mid 40s, late 40s, but we started going commercialized with them in the 50s. And
Mhm.
we put so many on this country in the 60s and the 70s that by the time that we got into the late 80s, we started getting into much more advanced forms of technology and compute. But by then, we also recognized we had to connect all these devices. So we started adding fiber from one part of the country to the next. And we used the right of ways of all the railway systems to do that. Not all, but most railway systems have some element of fiber running along the path.
Right.
But we connected everything with the hub and spoke backbone of the United States, and and then we we got to a certain point where we outlasted everybody because we had connectivity from one side to the other, and we had all the power that we needed. The utility providers were giving us all we needed. So if you're a data center owner operator or an enterprise end user, you just needed to go negotiate with your grid. Those days are over, right? So not only that, but you have China, who has some parts of their country stuck in the Stone Ages, and then other parts of the country that are so saturated and dense that they can't run fiber from one side of the town to the next because it's just overpopulated, right?
Right.
But what they're doing is kind of fixing those challenges, and then they're adding a whole pile of energy behind that
Yeah.
effort to support the assumed adoption rate of emerging technology coming from that part of the world. People don't realize that 2/3 of the world's population is in Asia, between India and China, and there's a lot of horsepower. We 75% of the world's manufacturing is outsourced there. 80% of the pollution comes from there, right? So, like, we have to figure out a way to manufacture more stuff here. Plus, we have to be able to maintain our dominance on AI, because it's not just a consumer technology or a technology for business. It's to optimize efficiency.
Right.
It's the most advanced weapon, machine, and tech ever built.
Right.
And we're going to have to look at this from a national security perspective. So, what's your thoughts on that?
So I think backing up slightly, first of all, I think uh, your history of how this developed is spot on. But there was one piece of it maybe that you didn't talk about, which was that every step along the way, there was a public-private partnership that worked together in order to move through different
Iterations.
iterations and break through different challenges, right? So, for instance, the internet itself was developed by DARPA, right? Because of the military communication needs, effectively, right? And then it was put out to the universities, right, which allowed tremendous amounts of innovation. And then, moving forward. After that, we saw this huge use of an investment by the government in computing, for instance, at the National Laboratory. So one of the reasons why we have, for instance, GPU-based computing today that is really the driver of a lot of our AI infrastructure is because the National Laboratories put tremendous amounts of investment into Intel, NVIDIA, AMD in order to build the biggest supercomputers in the world for doing scientific simulation, right? And then that spins out and has impacts out into the public world. And so we've always had these different public-private partnerships along the way, and I think it's going to be the same way going forward. And that's where, again, kind of our differences with China are going to help us stay ahead of them, because we have created an environment where the government can work together with private industry to accelerate deployment of a particular technology, and then let the private industry take it over and make it better and take it and make it bigger and have all the impact that private industry can have, right? Versus China, everything is, all done by the government. So I think that continued model of private industry working with the government is going to be the thing that's ultimately going to enable us to continue to accelerate this AI curve.
Do you think that we'll be able to get ahead of these challenges that we have before China achieves some dominance over us?
I think that's hard to say. I think we just got to work hard at it, really. I think that we need to keep all of our best brains on it and work with all of our amazing companies that are also innovative across the US. And yeah, I think we can stay ahead.
So use your crystal ball for me
Mm.
and tell me what you predict. When will nuclear be more mainstream?
Yeah, that's absolutely. And this is something that we talk about all the time, because obviously the need for electricity for AI is yesterday, like last year, right? And as I said, it takes a while to build a nuclear reactor. Okay. So right now, what we've got is we've got some of these demonstration reactors going on. They're going to start generating heat or electrons in the next 3, 4, 5 years. Okay. So that's about how far away we are on those first of a kind things really getting started up. But then by 2030, you're going to start to see really the start of commercial installations of nuclear reactors. Um, and many of those are going to be in service of data centers. So, for instance, Amazon recently led a round of investment into X Energy for $700 million ultimately in order to power Amazon data centers with X Energy's nuclear reactors. Those are going to be coming online all throughout the 2030s. right? And so we're going to see this ramp up across the 2030s of using all the various types of nuclear reactors. Maybe not every single one that's under development by all of the whatever 20, 30 different startup companies
Is
today.
that how many there are
Yeah,
now?
there's a
I
bunch.
remember there was 4 or 5 people
No,
talking.
yeah. No, we're talking about a bunch because there's a bunch of different niches, there's a bunch of different types of technology. And so, there's a and this goes back again to the innovation in the private industry in the United States. You've got all these different players, and then ultimately it's going, the best ones are going to shake out and build reactors. So whenever it comes to data centers though, what I like to say is, yeah, they need electricity next year and the next year, et cetera, right? And we're not going to be there with nuclear reactors yet. But it's not like they're not going to need electricity through the 2030s, right? And we're not projecting their need for electricity to start going down anytime soon. And as AI continues to infiltrate every single part of society, we're going to continue to need to power these things. So, if you want reliable, resilient electricity through your 2030s as a company, you should be getting on someone's order book right now for a nuclear reactor.
It's funny because you could be like, "I don't want nuclear reactors." Then you have to be like, "Okay, in 2030, you're ready to hand over the lead that we have in all areas of technology, including AI, over to another country."
Yeah, going back to the security aspect that you mentioned just a minute ago, I do believe that a reliable, resilient grid here in the United States is key to our national security, right? And for so many different reasons. And um, more and more as AI again gets embedded in every part of our life, it's also getting embedded in every part of our government, in every part of our military, et cetera, right? And these AI data centers are going to become important critical infrastructure for our country to operate, right? And one of the things that we're trying to do at the Department of Energy is make sure that the deployment of these AI data centers happens here domestically. If we don't provide the power and the grid and everything and fiber
They'll go
and
somewhere else.
everything, those companies are going to go somewhere else, right?
Yeah, if we don't provide the demand for those reactors, groups like Westinghouse will have no business, but no option but to go overseas. And
Well, on the nuclear side, they'll go other places, but also we'll see data center vendors going other places. Right now,
true,
it makes
because they don't
sense.
have power here, they'll go somewhere else.
Exactly. Right now, it makes sense in the United States because of our density of fiber and our availability of electricity, et cetera. But the moment we can't get them on the grid fast enough because of interconnection queues, the moment we can't power them because we don't have the nuclear reactors ready, we're going to start to see those installations go to other countries. And that's going to eventually become a national security issue
Oh, the
where
minute it
we're
happens,
running a large portion of the country off of data centers that exist outside of our country, right? And so that's one of the critical pieces here is that for the continued security of our country, we have to be successful. We have to get nuclear reactors rolled out, and we have to build the AI infrastructure to go with them.
so walk us through how you see the next 5 years unfolding for nuclear in the United States.
So there's going to be, first of all, a lot of collaboration between places like the national laboratories and all these nuclear startups. As their designs get finished, they're going to be building some of the very first reactors at the national laboratories. Next, I think you're going to see some rollouts that um, are happening at key areas in the country. Texas is one of those, having such a big interest in both data centers and nuclear energy. Right, they're building how many different reactors over near Texas A&M now? I don't remember, like
Yeah,
6 or 7.
really?
Yeah, they just created a whole new like reactor innovation center. I
At
apologize. I,
A&M?
I should know more about it, but I don't remember the details right now. But Texas is big on nuclear energy right now, and so I think we're going. And Abilene Christian, for instance, has been working on building a nuclear reactor there for quite a number of years, in collaboration with University of Texas here. So we're going to see some places in the country kind of adopt this faster than others, and I think that we're going to see the use of federal lands start to increase as well, because
Interesting.
because a lot of the siting that happens for large infrastructure projects in the country goes through federal regulatory processes, right? And so there might be an opportunity to utilize federal lands in order to streamline
Oh, yes.
regulatory processes to get nuclear reactors built faster.
So you don't have the pushback from the local community because it's already on federal land?
It's already on federal land. It might even already be on federal land where we've built nuclear reactors in the past, for
And
instance.
yeah, that makes a ton of sense.
Or had other nuclear activities like
But then
like fuel processing or those types of things happening in that area as well. And so you would actually have a supportive community because they've been working in that type of environment for a long time.
it would tie back to whatever transmission limitations there would be coming from out of that market, right? So wouldn't it just be better to go to places where like coal plants were shut down and in those, like, the infrastructure is there, the substations are there, the transmission lines are there, and just build a SMR there? Like you said in the very beginning, it's just a different form of energy. It's just a different form of heat.
Absolutely.
And then that way we could utilize the existing transmission lines that are already existing.
Yeah,
That's the only way to
there's
get
definitely
power.
going to be some of that. So the project going on with TerraPower in Western Wyoming is doing exactly that. They're building in the same area where there used to be a coal plant, right?
Yeah.
So they can reutilize some of
That
that
infrastructure.
infrastructure. And in fact, I know that some of the data center companies are also looking at
Yeah.
those similar types of sites for similar reasons.
Yeah.
Why, right? Even if they're not planning on putting energy generation locally, they could still use the interconnection capabilities at some of those sites.
I think a lot of them are. They're going to go natural gas. They'll sell it back to the grid. They'll use it for frequency response or on demand as needed. And I mean, Texas turns out has the largest deposit of natural renewable resources. So there's so much natural gas here. Like I said,
Yeah.
they're flaring a gigawatt of power a day easily, right? And so, like, why wouldn't we just build to that area for the bridging between now and 2030 when you're predicting, or when the Department of Energy is predicting, when we will start seeing the more the commercial embrace of nuclear, right?
Right.
Because it just takes time to recondition people, to change the optics and how they view it. Because right now, a lot of them grew up like me, Gen X. I mean, baby boomers are now being outflanked by the Gen Zers in this world. Gen X, like my generation. I think you said you were a millennial generation.
Just barely.
All right, but we're right there. We're in the meat of it right now, right? So I think that we have a desire. I think technology gives us more transparency and visibility into things, and it should help us build these things faster.
Yeah.
Don't you think?
Yeah, absolutely.
And de-escalate the conflicts between humans that don't understand what happens, how safe they are, and what happens if we don't do it because there's no alternative, right? What's the only alternative to nuclear? Larger solar?
Yeah, a tremendous amount of land for solar.
Yeah.
Geothermal is continuing to be on a rise right now as well, including things like enhanced geothermal systems, EGS. There's a lot of really innovative things happening there. But whenever you're talking the energy density needed for data centers, it's hard to see how we're going to have any large rollout of AI infrastructure in the U.S. without nuclear reactors to go with it.
All right. So I know that this is kind of part of the podcast where I try to bring it home, but what are you optimistic? Are you hopeful? I am too, man. I
Yeah,
really
yeah.
feel like it's only a matter of time. It sounds like over the last 10 years, people have gotten out of a defensive posture on all things nuclear, and now they're listening more. Would you agree?
Absolutely. It's a whole bunch of things coming together. We've had research going on at our universities and national labs on all these new types of nuclear reactors for the last 20, 30 years, right? That's matured to a point where it's ready to come to the commercial market right at the same time that we have a huge increase in electricity demand for AI infrastructure. And then, as I've said multiple times already, and I'm probably, repeating myself a little bit too much here, but the impact that AI is going to have back on nuclear energy is also going to accelerate
Improving
this
it.
entire endeavor, right?
I can't wait.
And so we're really going to see these two things, in my opinion, take off together.
Symbiotically. I
Yes.
agree.
Yeah.
What else have I not asked that you think is really important? Maybe it's just from a technology basis, or it could be national security basis. What else is worth noting, or you feel is worth mentioning to the people that are listening?
So I think going back to the what can the government do? I do think that there are a couple of important pieces of tax code and incentives, going back again to those public-private partnerships that are in place right now that the industry knows need to stay in place in order to continue to foster nuclear energy deployment. And Some of those are tax incentives, such as production tax credits and investment tax credits for nuclear energy that are available right now. And then other things like the Loan Program Office and DOE, which is giving out, which is providing loans and loan guarantees for some of these huge infrastructure projects like nuclear reactors, right? There's some of that government backing that is really going to help in order to get these first of a kind nuclear reactors built. Now, once we get the first of a kind built and we start down that learning slope and we know how to build them, they're coming off the manufacturing lines, then government can step aside and let the private industry completely handle it. But just like with supercomputing and just like with the internet, right now we do need the government to be involved to help us kind of get over this first of a kind hump and get all these reactors rolled out. And so I do hope that that continues within the government.
This is exciting. I don't see a future of AI without nuclear reactors.
Yeah, it's really hard to imagine. I mean, whenever you hear numbers like 4 or 5 gigawatt
Oh
like
yeah.
campuses, I mean, I swear every week that number gets bigger.
Someone
Every
told,
week I hear of a bigger deployment somewhere, right?
well, think of it like this. If you do the math on what all we've deployed since the genesis of this, let's say since 2000, someone had told me that in the next 5 years, we will deploy more in the next 5 years than we've ever done, perhaps. So that's like every time that I've been in this industry, it's grown at a double-digit CAGR, and people are like, "This is incredible." I think that it's going to change the labor force. I think that there's a lot of kids right now that are graduating college already with a degree that's obsolete because of technology, but I do think there'll be, I mean, people go to the military, they go in the trades, they go into this, they go into that, but I do think there'll be an incubator for where people could go and just be certified on the delivery side of the power of that needs to feed the data center itself or the data center
No
itself.
doubt.
That's where we're headed.
The workforce is absolutely critical component in this. We won't get there without a skilled workforce. So, again, the government's doing a lot of things on that end to help train up the populace. But that's one place where really interesting new ideas could really have a big impact as well, and partnerships across different trade groups and things like that. Could make a really big difference. So. Yeah, all these things need to work together. We've got to have the technology, we've got to have the companies that come through with the designs, we've got to have the regulatory environment, we need to have large off-takers like the hyperscalers and chip fabs and others, and we've got to have the workforce. So we've got to have all these pieces come together, and that's exactly what the Department of Energy is working on right now, is coordinating all those pieces in a cohesive whole that can actually deliver this next set of energy generation capability so that we can build out AI data centers.
So anyone that's listening to you right now, how can they find you on LinkedIn?
Yeah, so I'm Derek Gaston on LinkedIn. Yeah, you'll find me if you search for Moose, which was one of those software projects that I mentioned.
Yeah.
If you search for Moose Derek Gaston, you'll get a whole bunch of me all over the internet.
Oh, nice. Well, I don't think they'll have to do that, but I do like, this is the first time you and I've talked. We're actually speaking tomorrow at South by
Yeah.
Southwest together. But I also want you to consider coming in and packaging something like this. I won't go 2 hours deep, but we host a conference in Austin once a year at ACL, Data Center Anti-Conference, and this is the Data Center Revolution. So this is a podcast platform that lets us get to people that are driving to work, people that are working out at the gym, but there'll be people that are going to come to that stage, and hopefully we could pick apart a little bit of time where you could continue to unpackage this. And between now and then, I'm hoping that people reach out to you, probably have a few questions.
Yeah, absolutely.
Look for the trends, look for the patterns, because you're on the inside looking out, we're on the outside looking in. So everything that's intuitive or understood or just assumed by your side is going to be a blind spot for us. Just like on the data center side, there's certain things that are just intuitive to us that we understand. That I sat at a dinner last night in Midland, and I sat next to an incredibly smart person who explained a lot of things to me that I never understood about that side of the industry.
Yeah.
And simultaneously, I was explaining to him the basic differences on data centers, the differences between cloud, the difference between AI or the Internet of Things. And each of those have a different requirement, right?
Right.
But what we're really focused on right now is AI. So listen, anything else you want to mention or wrap up before we let it roll?
just what you said. Feel free to reach out to me. As you can tell, I like to talk, so I'm willing to talk to anybody, especially about nuclear energy. I'll talk to anybody.
Yeah, because there may be people that want to have you come speak at their events or speak at their
Yeah,
teams
absolutely.
or just otherwise connect the dots with them to these other groups. So I know I, for one, maybe would love to have an X Energy or something like that on our stage one year. Just can you believe it? We first started in this industry talking about space power and cooling and nothing else, and then all of a sudden densities got bigger, and then we're building bigger data centers, and now we're talking about the power plants that go with these things. And now
Yeah.
we're talking about nuclear reactors.
It's incredible.
It's incredible how this industry has iterated and evolved and shifted. But
Absolutely incredible. Last thing, I'll put in a plug for the Department of Nuclear Energy.
Yeah.
I mean, the Office of Nuclear Energy and the Department of Energy. We have a tremendous amount of resources online. There's a blog, there's an X account. We really keep up with all of everything that's going on in nuclear energy, and a lot of that has to do with data centers. So if you have any interest in this area at all, get out there. There's tons of resources that say all the same things that I was saying today. So.
Well, listen, man, this is awesome. I appreciate it. I'm looking forward to hanging out with you tonight. We have the panel tomorrow. It's going to be amazing, and this is important, man. This is a complicated topic.
Yeah, it is.
This will be the last time we talk about it.
Hopefully this helped a little bit.
Yeah.
And then we'll have more conversations.
Well, we're going to publish this, and then if you're listening, please like and subscribe to the channel. But please post a comment or post a question so that Derek could jump in and help demystify some of these things, because
Absolutely.
I think we grew up thinking that nuclear was so far away, and here we are today going, it's here and it's now, and we need it now.
Now's the time.
All right, man.
Absolutely.
Well, listen,
Yep.
Thank you for joining
No
the
problem.
revolution. I appreciate it, man.
Yeah, no problem. Thanks for having me.